Yeah, so in this video I'm gonna show you how we can implement a perceptron in Python using NumPy and PyTorch. So I will be using Jupyter notebooks because I think for simpler code examples it's actually quite nice to use Jupyter notebooks because I can execute one thing at a time and it will make things easier to explain. However, later on in this course we have to, I think, move to Python script files because when the deep learning models become larger and larger, managing them in Jupyter notebooks can be a little bit, I would say, tedious and also dangerous because it's easy to lose the overview and debugging is a little bit harder if you have these separate cells and stuff like that. And then the danger is that you might execute things out of order and also you want to import certain aspects from different files. You don't want to have everything in one notebook because then it becomes really confusing and unmanageable. But we will get to these parts later in this course. So back to this topic of the Perceptron implementation in NumPy and PyTorch. All the code files are actually on GitHub, so if you go here to this link, or I will also link them on Canvas so that you can just click on them if you are interested to play around with them. The homework will be based actually on the NumPy one, where I will ask you to implement this in plain Python just to make sure you understand what's going on, and by converting NumPy code to Python, I think you will work with the code step by step and get a better understanding of these individual things. And I think also going from NumPy to Python is easier than from Python to NumPy if you are relatively new to NumPy. So in that way, let me now walk through the NumPy notebook. The PyTorch notebook is actually very, very similar, which is one of the cool things about PyTorch because it is very similar to NumPy, except there are some extra features that we will be using later on. And I will have a lecture on PyTorch where I will explain you these differences. So for right now, it doesn't make such a big difference whether we use the NumPy or PyTorch notebook. I will also show you a step-by-step comparison after I explained the NumPy notebook, so you will see what's actually different between the two. All right, but let's do one thing at a time. So here I will make this a little bit bigger. I hope it's easier to see then. It's maybe almost too big. I don't know. Let me see. All right. So I'm starting here. Let me clear maybe the outputs and then I will execute them one at a time. So I'm importing some libraries. For those who have not used notebooks, this one here, this command is for showing plots in the notebook. It's technically not necessary anymore always. Sometimes on some computers, plots will not be shown in the notebook if you don't include that line, and it doesn't hurt to include that line, so I always do this. Here I'm just loading the dataset. So there's nothing really interesting happening here, but I will step through this step by step. So the data set is like some toy data that I generated. I will show you how that looks like shortly. So here I have two feature columns. I didn't include any column header, but this is the first feature, this is the second feature value, and this is the class label here. So there are zeros and ones. And you can see the data set is not shuffled, and actually it's helpful for learning if the data set is shuffled. It will make the learning a little bit faster in the Perceptron. All right. So here I'm loading the dataset into NumPy. You can also use pandas, but I thought it might be overkill because it's a relatively simple dataset. And then I'm assigning the features to X, which is a matrix then, and Y, which is the class label array. I can maybe show you just how they look like. So this is X, it's a matrix, and Y is the class label array. So here it's shuffled because I actually executed this whole bunch of code. So you then can already guess what's going on here. So here I'm loading the data and then just printing some summary information. It's always, I think, a good idea to do that to get an idea. So we have 50 labels from class 0 and 50 labels from class 1. We have thus 100 data points in total and 2 feature columns and also 100 labels. So for example, here we can see, okay, these and these numbers match, so that's what we expect. It's just some sanity checks here, some making sure that everything looks okay. Then here I'm shuffling the dataset so that they are not all in order, they are shuffled. And how I'm doing that is I have to shuffle X and Y together, right? So otherwise everything will be mixed up, then the features won't correspond to the class labels anymore. So how am I doing that is I'm creating a shuffle index. So I can just show you. Creating this shuffle index here. And how it looks like is it's just the numbers from 0 to 99, so the 100 indices. And then I'm actually shuffling these indices. So here I'm generating a random number generator, and then I am shuffling these indices here. So you can look at these after shuffling. So after I execute that, you will see, oops, execute that. Well, oops, that's too much. But you will see they are now in random order. And then I'm using that to select the data points from X and Y. So then X and Y will be shuffled based on this shuffle index here. So that's how we shuffle. And then I will use the first 70 data points for training. And the last 30, so we have 100 data points, so 70 to 100. The last 30 data points will be for our test set. Later on, we will be seeing or using more convenient ways to load data in PyTorch. So there are some loading utilities. Here I'm just doing it step by step so you get a feeling of what's basically going on. And then I'm normalizing the data. So this is sometimes also called standardization. So here I'm standardizing the data such that after standardization it will have mean 0 and unit variance. So I'm subtracting the mean and divide by the standard deviation. So here I'm computing the mean and standard deviation of my sample. And then I'm subtracting the mean and divide by the standard deviation. And then both will be having mean 0 and standard deviation 1, so unit variance. So you can actually check that. Oops. It's not quite true because we have to look at the training mean. Okay, they're very close to 0. So this is 70 digits after 0. So 0.0000 something up to 2. So very, very small. It's almost, it's identical to 0 essentially. And then for the standard deviation, it should be around 1. Yeah, so the data is standardized. Why am I doing that? It kind of speeds up training a little bit. It's like stabilizing the training. For the Perceptron, it's not that necessary, but it is a good practice to do that for other types of optimization algorithms later on when we talk about stochastic gradient descent. So this is something, standardization, that is usually recommended. The only types of machine learning models where this is really not that necessary is like for tree-based models. That is something we covered in, that I discussed in statistics 451 when we talked about decision tree algorithms. These don't require standardization, but all other machine learning, deep learning models I know, they can usually benefit from that. Like especially stochastic gradient descent will just learn faster, which is something we will be doing later. So it's just a good practice. All right, let's take a look at the data. So here, this is our training set, how it looks like. So you can see it's around centered at 0. We have two classes, class 0, these the circle here, and then the square for class 1. So feature 1 and feature 2. That's our training set. And so these should be 70 examples, and then the remaining 30 examples in our test set. So what we want to do is we want to train our model on the training set and then evaluate it on the test set. So let's implement our Perceptron model then. So here is the Perceptron code. You can see it's relatively short. I'm implementing it using a forward and a backward method. Why I'm doing that is because that is also how things are done in PyTorch, and it will make things more familiar later on if I start using this habit. All right, but let's start at the top. So I'm implementing it as a class here. And you should be, I think, familiar with Python classes. So here what I'm doing is I'm running in a constructor. So this is a special class method, a constructor. I'm giving it the number of features because that's what I need to know the number of weights. And I'm using here the implementation where the weights and the bias are separate because that is more convenient, so I don't have to modify the feature vector. So what I'm doing here, if I go back to my lecture slides, I'm using this this notation here where we have the bias separately. So I'm initializing the weight vector and the bias unit. So the bias unit is just a single value. It's just one number. And the weight vector, it depends on the number of features, right? So I make this a column vector, a row vector. So this is then this equal to m, the number of features. All right. So here I'm just setting up my weights and bias. I'm setting them to 0. Later on, for certain algorithms for stochastic gradient descent, it's better to initialize them to small random numbers. Here for the Perceptron, it's not necessary, but for neural networks, it will be necessary later on. We will see that. In the forward method, I'm computing the net inputs, actually here in linear, and then I'm predicting the prediction, computing the predictions. That's my threshold. So this is the net input. I'm calling it linear because later on we will also see linear layers in PyTorch. They are called linear, and they are basically computing the net input. So this is, you can see the dot product between the input vector and the weights. So that is computing this part here. And then I'm adding the bias here. I can actually make this bigger. All right. Then here we have our threshold function. This threshold function is just using NumPy where. So how this works is it's saying if linear, so if the net input is greater than 0, then output 1, otherwise output 0. So it's our forward method. And here is our backward method. So the backward method, why am I calling it like that? It is for computing the errors. So usually when we have deeper neural networks, we will use something called backpropagation, where we look at the outputs, and then based on the outputs, we adjust the inputs. So in that way, we run the forward method to produce the predictions, and then we compute the errors and then update. So it will become more clear when we have a deeper network where there's really like a backpropagation going on. So these are our two methods. So backward is computing the errors, which is the difference between the true class labels and the predictions, and forward is used to get the predictions in the first place. Let me see here. So this is what we just implemented. So we implemented here the prediction that's going on here. The prediction is equal to step A, and then step B is the backward pass which gives us the errors. And now we have to put everything together. So I implemented a train method here. So so this train method is basically the whole thing here. So for epoch, in the number of epochs, so this is for every training epoch, and then for every training example, this is here this part. We perform the forward path, backward path, and update. All right, so since backward is already doing our forward, we just call backward here. There's some ugly reshape here going on, and that is because making the vector dimensions match. Otherwise you will get some errors. So here I'm just making the dimensions match. You can let's take a look. So here this will be 1 row and m columns. So it will be I think this is called a row vector. I said earlier the other one was a row vector, but I'm always confusing the words row vector and column vector, because here this is just one row and multiple columns, but this is because there are multiple columns, but it's still called row vector because it looks like a row. Anyway, so here we have this row vector here, and this has to have the same dimension as y. So in this way, I'm just making this the same dimension, so you can compute everything nicely. Otherwise you will find there will be a dimension mismatch. So it's just a reshaping going on here. And then here we perform the update. So again, I'm doing the reshape afterwards so that we get the original dimensions back, because the weights here, they also have the same. So see, we are matching the original dimension, so we're just reshaping so we can add to it. Otherwise there will also be a mismatch if this is just a single number, or if it's a 1 times m vector instead of a m times 1 vector. So yeah, this is a little bit annoying to do this reshaping. Technically it would also, I think, not be necessary if I remove the dimension from everywhere, but here that's more explicit actually. Doesn't hurt. It's just like, you have to be aware of that. And then also we update the bias. So the bias, it's just updating it by the errors. The reason is, think about it, if we would have a 1 here, where's my figure? If I have a 1 here, so this would be 1 times the bias unit instead of, so the input would be the 1, right? So instead of saying errors times the feature, we would have error times 1, right? So error times 1, and we can cancel the 1. So instead of writing it like this, since we have the bias separate, I can just cancel this so we don't have to include that. Then next, evaluating it. So evaluating the performance. Here I'm just doing the forward pass. And then compute the accuracy. The accuracy is computed by checking how many of the predictions match the true label, and then divide by the dataset size. So it will be giving me a number between 0 and 1. All right, so this is my perceptron. And then here I'm training it. So here I'm initializing it and then training it for 5 epochs. And then I will print the model parameters afterwards. It's pretty fast. So we get the weights, the weight vector 1.27, 1.346, and then the bias is -1 in this case. And now we can evaluate it, compute the accuracy. So the test set accuracy is 93%. It's not quite 100%. On the training set, it should actually have 100%, right? Because it's linearly separable, this data set, and it should converge if it's linearly separable. So let's do that. Yeah, that's 100%. Everything is classified correctly. Test set is not as good because we may overfit. So let's take a look at the decision boundaries. So here is some complicated code to compute the decision boundaries. It's actually not complicated. What I did is I rearranged things here, right? So what we have is, if you think about it, the decision boundary is greater or equal to 0. So everything hinges upon 0. So if we have our computation, it's x0 times w0, right? Plus, that's our net input, x1 times w1. Let me, that's correct. Let me just wanted to bring that a little bit more closer together. It's easier to see. And then plus the bias, right? So this hinges upon 0. And now let's see, so what we're interested in is, what we're doing here is we are taking one fixed number. So let's say we're taking, for feature 0, a minimum value of -2. So we are going to the left-hand side here. And then we want to find, so this is for x0, so x0 is the x-axis and x1 is the y-axis. So we take -2, this data point here. Or actually we are here, we only know -2, and we want to find the corresponding x1 value. So this is x0, so it's at -2. So what is the corresponding x1 value? So we have to rearrange this, solving for x1, right? So what we do is we move this stuff and this to the right hand side. So we have x1 times w1 equals to minus x0 times w0 minus b, right? So I'm just subtracting this and this. So it's now on the right hand side. And then I want to know x1, right? So I divide by w1. So when I divide this, then so this is basically essentially what I've written here. So I get the x1 value. I'm calling it min. The reason is because it's the left hand side. Then I'm doing the same thing for the right hand side. So here I'm doing it for the right hand side. I'm again setting x0 to some value. I'm setting it to 2 here, and then I'm finding the corresponding y-axis value, which is this x1 max here. So I'm doing the same thing, just rearranging. Now I'm using a max value, and then I'm connecting these lines, and that's how I get this. I've done this here for the left hand side for the training set and right hand side for the test set. So yeah, one is the training set and one is the test set. Okay. So this should be, yeah, the it's maybe easier to write it like this. The decision boundary doesn't change actually, because it's the same for the training and test set. Just the data set is different because the decision boundary only depends on W, right? So we are providing, these are fixed values, we are providing them, and the decision boundary only depends on these parameters, on the model parameters, so the decision boundary does not change here. So this is for the training set, and this is for the test set here on the right hand side. And you can see in the training set case it perfectly classifies these examples, and on the right hand side this is the test set. You can see it's maybe fitting some of the data too closely. I mean, there's no other way actually, but it happens that here in this case it doesn't perform well. Actually, yeah, there is a different way. If you would fit the boundary like this, like this, more straight, then you may get these right, but it just happens so that these data points are not in the training set, so the model doesn't know that it should shift the boundary more to the right here. So in this way the model does actually a good job on the training set, but on the test set, yeah, it's not so good. So in that way it's actually, this term is called overfitting, because it fits the training data a little bit too closely and doesn't generalize so well to the test set. Okay, so this is how the NumPy code works. In the homework you will be playing around with this a little bit more, and then re-implement that in just regular Python, just removing some of the dot products, replacing them by for loops and so forth. Yeah, the PyTorch code, I don't need to talk about this, I think, because it's the same. So this is exactly the same, this is exactly the same, this is exactly the same. There are some differences here, but yeah, this is exactly the same, this and this, except that I'm now using torch tensor instead of NumPy arrays. But yeah, I prepared an overview here to show you the main differences. So in class we will be talking about this in more detail when I talk about PyTorch in, I think, next week or in 2 weeks, depending on how far we get next week. So here I highlighted the differences though. It's also in the it's from the slides. So on the left hand side this is the PyTorch implementation. On the right hand side is the PyTorch, sorry, NumPy and PyTorch. And you can see there are not that many differences. So the way the weights and biases are implemented here, we are using NumPy zeros. Here we are using torch zeros. We are a little bit more specific here. Instead of saying NumPy float, we say torch float 32. It's a 32-bit. I have this device here because the way I implemented things, it would also run on the GPU if there's a GPU available. If no GPU is available, it will use the CPU. So there's this device here, which is provided here optionally. It's not necessary though. And what's a little bit more, it's a little bit different. So here, I mean, there are multiple ways you can write that. You can also use a plus function, to be honest. I just happened to use torch.add, but I could have also used a plus. So what I mean is I could have, I don't know why I actually did it so complicated. I could have just added a plus here and removed this torch add. It should still work. Yeah, and then the MM is matrix multiplication, and so NumPy we usually write dot, in Torch we write, or PyTorch we write for matrix multiplication. But in PyTorch, the dot function can also do matrix multiplication. So in a way, it is kind of like the same thing. It just looks a little bit different. The where function in PyTorch is a little bit more, I would say, involved. Not that much more involved, but it has to have placeholders. Instead of having a 1 and a 0, it needs to have a tensor here. So I'm creating this as placeholder here and providing them, but it's the same concept. And then what's a little bit different here is the last part. So instead of numpy.sum, it's torch.sum. Here I'm converting it to a float, because otherwise it will be an integer, and then integer divided by some value will give an integer. But we want to have a float because it's a fraction between 0 and 1. So if you don't do that, you will get back an integer, and that's not correct, because the value, the accuracy is a value between 0 and 1, which is why I'm casting this to float. But again, the PyTorch code will be covered in class in more detail later. So yeah, that is what I wanted to say about the code. You get to play around with that a little bit more in the homework. Then here, for the optional convergence theorem, I wanted to make a video about that, but I realize I talked a lot about the code right now, so I honestly want to wrap up this lecture. The next video will be probably short, so that in the next week we can start a fresh topic. So then we can talk a little bit about the linear algebra background for deep learning, some notation, a little bit about calculus, and then get started with PyTorch next week. So in that way, I think this is not really necessary. So this is some optional mathematical proof. I will leave it in the slides because I spent a lot of time making this. But yeah, you can read through that, but it won't. So if you don't know about that, you won't miss anything because it's not relevant for deep learning. It's just showing that the perceptron will not converge if the data is not linearly separable. And you can try that out in practice. So you can, for example, if you go to the animation here, this is the animation that I showed you in class. It's just as a Jupyter notebook. And you can change the data such that one of the blue points is here. So you can change the class label of one of these points, or you can change the class label of one of these points, and then you can run this and you will see it will never converge. So here this one will converge eventually at iteration 49. But if you change one data point such that it cannot separate the data correctly, it will go on forever essentially. And this is what the proof is about. So you can mathematically show that there's a lower bound and an upper bound for the size of the weights, and based on that you can basically conclude that it will converge only if the classes are linearly separable. So I won't go into too much detail about that, when it will converge. So this is showing that it will converge if it's linearly separable, but only if it's linearly separable. And yeah, in the last video, let me talk about the geometric intuition about the decision boundary. So again, don't worry about the convergence theorem. All you have to know is that the code will run forever if the data is not linearly separable, and otherwise it's guaranteed to find the solution. So it's guaranteed to find this boundary if it exists. That's what the proof is about. All right, so next video, the geometric intuition.